Hey guys, here is your intro to the alternating series test. Okay, this is going to be one of those sort of automatic ones, and that's why I thought it would be a good one to just kind of do on your own. These are the most obvious ones to recognize simply because they are alternating. So a basic one would be something like -1 to the n plus 1 of 1 over n. So if I took away the alternating part, this would just be our harmonic, right? And we already know that that diverges. But what happens when we make this an alternating harmonic, right? So what would that look like? Let's see, our first term would be positive, so we'd have our 1. And our second term would be negative, so that'd be minus a half, plus a third, minus a fourth, plus a fifth, etc., etc. Okay? And the question becomes, is that enough to make this series converge? Our original harmonic obviously diverged. We proved it in like 15 different ways. But the alternating one is interesting because you start out with 1, but then you actually subtract a value. Okay, you subtract a half, but then you add a third, then you subtract a fourth, then you add a fifth. And each time you're adding or subtracting a little bit less than what you did before. Okay, so for the alternating series test to work, we have to satisfy two conditions. The first condition is, first of all, you're really just looking at the n term, the a sub n, although we call it b sub n for the purposes here because a sub n is actually the whole thing. So b sub n, oh, that happened before. Let's not do that. So the b sub n is just the term that's not alternating. Okay, the whole a sub n term is everything together. So the first thing we need to happen is we need our n plus 1 term to actually be less than or equal to the n term. Okay, so if we go term by term, when you go to your n plus 1, it needs to be less than or equal to the term you had here. Okay, there are a couple of instances where they might actually be equal, maybe for the first couple, but at some point this is what's going to happen. You're going to end up with a value for your next term that's less than the value from before. Forget the plus or minus. Remember, I'm only focusing on the b sub n. Okay, that's condition number 1. And condition number 2, we've got the limit as n goes to infinity for b sub n needs to be 0. This is essentially our gateway test, right? Remember, our gateway test was the limit as n goes to infinity for the whole thing had to be 0 for us to even have a chance. If it wasn't 0, then this would diverge. So if we satisfy this condition, we're just focusing here, and as long as the terms are decreasing, then we have the convergence. So then the series converges. Okay. So what do? Well, first of all, you need to make sure that the b sub n is decreasing. Okay. So we'll do that. Sometimes you got to go old school to show decreasing, and since we already know how to do that the old-fashioned way, I'll show you here. So to show decreasing, let's sort of look at our b sub n term as if it was a function. And to show decreasing, obviously we look at our slopes. The cat. All right, so f prime of x, of course, is, let's see, this is x to the -1. So this is negative x to the -2. So I have critical number at 0. So at 0 for my f prime. When x is negative, I have negative. When x is positive, I have negative. Guess what? This function is decreasing all the time. All I really care about is from 1 to infinity, so I'm definitely decreasing from 1 to infinity. Therefore, I've just shown that my b sub n term decreases. How about the limit as n goes to infinity? Well, that's pretty obvious to tell. 1 over n, of course, as n goes to infinity is 0. Therefore, the alternating harmonic, this is the alternating harmonic, actually converges. Sorry, converges by the alternating series test. Okay, so this is what you got to do. You really got to check these two. Sometimes you get lucky and the decreasing sort of presents itself in the problem. And this one would have been pretty easy to just say it decreases. But if you ever had to really justify it, you could always go old school. Okay, I'll do another example for you, and I think honestly that probably is going to be it. Okay, so let me pull another example out for you. All right, how about this one? Let's see. How about Okay, so these are just book problems, so it's not that big a deal. But let's make sure we satisfy both conditions. First of all, is it alternating? Absolutely, right? That's a clear-cut, automatic. Okay, I'm going to use alternating series test, and I need to check to see that we're decreasing. So, I mean, it seems pretty obvious that with the denominator the way it is, that it is decreasing. But let's be sure. If I turn this into a function, go old school. Let's see what I got, a quotient rule here. So x cubed plus 1 squared, x cubed plus 1 times 2x minus x squared times 3x squared. Clean that up a bit. Let's see, 2x to the fourth plus 2x minus 3x to the fourth. And let's see, I can combine those and then pull out an x, right? So this is going to be negative x to the fourth plus 2x. And then if I take out that x, actually I'll keep the negative inside. Actually, I guess it doesn't matter. I'll take out a negative x. So x cubed minus 2, right? X cubed plus 1. And my only critical number appears to be 0, or my critical numbers are 0 and cube root of 2. So 0, cube root of 2. Again, I only really care about numbers, 1 to infinity, but nevertheless, if I plug in 1, I get a positive. If I plug in a billion, I get negative times positive divided by positive is negative. So I've shown that f is decreasing when n is greater than cube root of 2, which basically means greater than 1. Okay, so I've shown decreasing. So b sub n plus 1 is less than or equal to b sub n. Satisfied. Okay, now I got to show the limit. Well, the limit as n goes to infinity for n squared over n cubed plus 1 is 0. Done. Okay, and that's basically it. Satisfy those two conditions, and you can use the alternating series test. Converges by alternating series test. All right, let me know if you have any questions. Talk to you guys later. Bye.